Okay, today we're going to be working on something that you should have learned back in geometry and probably even as far back as middle school math. We're going to be discussing square roots specifically, but we're going to branch that conversation out to deal with radicals as well, so that we can see what the difference is between the two and when we use them and how they're used together and so forth. This is going to be an important pre-lesson, if you will, to material that we're going to use in Chapter 5 as well as in Chapter 6 and 7 and 8 as well. So the skills that you learn in this little review document will serve you well for the entire second semester chapter of Algebra 2. Now, you have received a shortened version of these sets of notes in my class previously probably, and I've extended it to give you a little bit more practice and a little deeper understanding. So let's go ahead and start and take a look at what we're going to be dealing with here. We're going to start off with the understanding of raising of a value to a power. Okay, and so the power is represented by an exponent. So as you can see here, if we have x times x, we can write that as x to the second power. Now, if you recall, in the first semester of Algebra 2, we discussed about raising negative numbers to a power of 2 and how important it was to keep the negative value in parentheses so that you're actually multiplying the negative times each other so that you get a positive value. So that's going to be very important as we go forward here with the radical symbol. Now, if we wanted to reverse this process, so if we wanted to take the squaring process or raising something to a power, the way to undo that, so to speak, is with its corresponding root. Now, since we're strictly dealing with squared terms in Chapter 5 when we're working with quadratic functions, we're going to be working with square roots to undo the power of 2. Now, whenever we use a square root, we are being said to take the inverse property, which, if you recall, just undoes whatever it was, whatever property we were using before. Now, the square root sign is what a lot of you may refer to, is really called a radical sign. Now, this is important to understand the difference here. A radical sign a lot of times looks exactly like a square root sign, but as we're going to find out later in later chapters, that the radical sign actually takes on the number of the root given. So I'm going to give you a couple examples up here. The radical sign is actually the same thing as a square root sign in this regards. It's that 2 is understood to be in that little notch up there. Now, the sign itself, that kind of looks like an old division sign, it is actually called the radical symbol. We will use this radical symbol for all types of roots. So later on you'll see a third root and a fourth root and maybe even a fifth root. And as we said before, whenever we use the radical sign, we're actually using the inverse property, and basically a square root undoes a square, a cube root undoes a cube, and so forth. So we're going to focus mostly on square roots right now, as that's what we're going to be focusing on in Chapter 5. So let's take a look at how a square root actually works and how they cancel out powers with the same degree. As you can see in this little equation, the square root of x squared. Now, it's an understood square root because there's an understood 2 in the little notch. So I rewrote it with the actual root there. So if you see here, we have the root. This is the root, and we have the power, and that is the power or the exponent. And so if the root and the power are the same, they actually cancel each other out. Now, this will actually give us the absolute value of that term. And if you recall from previous lessons, anytime we have the absolute value of a term, we have actually we have the positive and negative version of that particular value. So we can see here that the square root of x is actually equal to plus or minus the square root of x. Now this is going to be important for us to determine in Chapter 5 when we're dealing with quadratics, because we're going to need two answers, and we'll discuss that as we go along. For the purposes of this set of review notes, however, we are only going to focus on the positive version of the root. So if we look at some just basic principles about square roots, we have 5 of them here that you need to be aware of. Negative numbers do not have square roots in the real number system. Now, this is going to be important. We're specifying the real number system here. Later on in Chapter 5, we will actually be dealing with something called an imaginary number, or the complex number system. So, again, we're only focusing on real numbers in this review section and positive values of the square root. So, some basic principles: 0 squared is 0, 1 squared is 1, and you need to just keep those things in mind. Now, we're going to focus on taking the radicals, or the square roots, and putting them in simplest form. And we did a little bit of this whenever we discussed Pythagorean theorem. And in essence, you need to know these 3 rules, if you will, very, very well. So, no perfect square under the radical, no fraction under the radical, and no radicals in the denominator. So let's take a look at each of those instances on their own and see how we would actually reduce those. First thing you're going to run into is something called a perfect square. So if we took a number like 2 and we squared it, we're going to get the answer of 4. So 4 is a perfect square because it is 2 being squared. If I wanted to undo that process, I would actually take the square root of 4, which is going to give me plus or minus 2. And again, we are just going to focus on the positive value. Now, one of the things that you will need to do, because in the 3rd quarter we will be taking some pop quizzes on specific values. So you need to know your perfect squares and their inverse properties, their square roots, from 0 to 20. And we will do this for a grade, and you'll need to create some sort of spreadsheet that I will guide you through a little bit later in the quarter. But just keep in mind, you need to be familiar with those. If you are familiar with those, they will help you tremendously on the ACT. So always looking for little shortcuts and little helpful hints that we can use on the ACT. Now, let's take a look at a problem that would actually use perfect squares. If the directions told us to reduce to simplest radical form, that means we want to break the radical up and put it in the smallest pieces that we can, according to the rules that we learned up here. So these rules are the rules that are going to judge whether we've done, whether we've put the radical in simplest radical form. So if we look at the square root of 36, it's an understood 2 for the root. Remember, 36 can be written as 6 squared, and that being the case, the root and the power actually cancel each other out. So the square root of 36 is the same thing as the square root of 6 squared, which these 2's cancel each other out, leaving us just the 6. Now, I do not expect you to go through these steps every time you do this. That is just to show you the step-by-step technical version mathematically what's going on. I would expect you to just know the square root of 36 equals to 6, and knowing all your perfect squares and your square roots up to 20. So if we look at sample problem 1, just go ahead and pause the video for a second and work part A, B, and C. Okay, so if we're working these and we've memorized them, that's the ideal situation. Otherwise, you may have used your calculator to help you with this, and we know that the square root of 64 is equal to 8. The square root of 169 is equal to 13, and the square root of 289 is equal to 17. Now, here's the thing. even though the radical is completely eliminated, we've taken a radical and we've simplified it as far as we can. So this is considered still to be in simplest radical form because it's simplified as far as you can go. Now, in some cases, you will still have a radical, even though it's simplest radical form. There may be a radical remaining in the final answer. So let's take a look at a couple other properties that we can use to help us with simplifying radicals. The first one is the multiplication property, or the product property, where we can take a value and break it up into two individual radicals. So if you look at part A, you can see that we can break 18 up into 9 times 2, which then can break up into two completely separate radicals. Whenever you use the product property, what you're really doing is looking for perfect squares. So you're going to look for perfect squares embedded in a number. So if we look at 18, we know that that has a number of different factors. You can break up into 6 and 3, 18 and 1, and also 9 and 2. So we would be looking for the factors that would include a perfect square, and that's why we would choose 9 and 2 so that we can break those apart. Now, keep in mind, the product property can go both ways. So if we have a 5 and a 10, we can actually put those together, which gets it all under one radical. Now, the only reason we would really want to do this is if we see that the potential product could be broken down into something different that actually has a perfect square, and in this case it does. The 50 can be broken up into 25 and 2, which has a perfect square of 25. So go ahead and let's take a look at sample problem number 2. You've got 4 there. And go ahead and take pause the video and take time to do that real quick. Okay, so if we look at this, square root of 75 has two factors that has a perfect square. One, we have 25, which is our perfect square. So if we break this up, I'm going to have 25 and 3, and I can break those into separate radicals. And the square root of 25 is 5. The square root of 3, however, cannot be broken apart any farther, so we would just leave it as 5 times the square root of 3. Now this is simplest radical form, so we would stop right there. Square root of 27 can be broken up into the square root of 9 times the square root of 3, which gives me 3 times the square root of 3. The next one was a little different because it has a variable in it. But if you think about this, 9 is being multiplied times x squared. So we can actually break those apart into two separate pieces, or two separate factors, and each of them is a perfect square. 9 is a perfect square of 3, so 3, and x squared, when you take the square root of x squared, the square root and the square actually cancel each other out, leaving you simply x. So we have 3x remaining. The last one here is one where the 2 and the 8, neither one of them are perfect squares, but if we put it together, we can see that it's going to give us the square root of 16, which if we've learned our perfect squares, we know that that equals to 4. So these are all good examples of the product property that you could use and see in different ways. Now we'll move into division property, or the quotient property. And if you recall back from our original rules, it says that no fraction can be underneath a radical. Well, this is a way that we can break that fraction into two individual radicals. Now the hopes are that we can get a perfect square in the denominator so that the radical disappears. Remember, that's another property, that you cannot have a radical in the denominator as well, so we'll have to address that issue in a second. But if you look at this first, if you look at sample A, you could immediately get past the second rule of not having a fraction under the radical by simply reducing the fraction, and in this case it just leaves you with a 3. So square root of 3 is perfectly fine because the square root of 3 cannot break down any farther. That is in simplest radical form. However, if we look at B and C, In part B, we do have to use the quotient property and break it up, and then we're fortunate enough that each of the individual parts are perfect squares, which creates a fraction with no radicals. Now, C is the more common example of what happens whenever you have a fraction under a radical. What tends to happen is one of the radicals will disappear, one of them will not. Now, keep in mind, square root of 6 is simplified all the way, but there may be situations where you still have to do some simplification to the radical. As long as there's no radical in the denominator, however, we're good. So let's take a look at a couple examples. Sample problem 3. So go ahead and pause and work A, B, and C. Okay, so if we use the quotient property, we can break these up into separate radicals. And if we look, square root of 81 is 9. The square root of 225 is 15. It's very important, however, that we reduce the final answer for it to be in simplest radical form. Even though the radical is gone, we still have to reduce fractions. So 9/15 actually breaks down into 3/5, giving us our final answer in simplest radical form for part A. Part B, we can break this up into the square root of 2 over the square root of 25. Square root of 2 is simplified. Square root of 25 breaks into 5, and since we cannot reduce the square root of 2 anymore, square root of 2 over 5 is our final answer. And then part C has a couple different things going on here. We've got the square root of 8 over the square root of 25. Now this is going to give us a square root of 8 over 5, which you would think that we were finished here because we no longer have a radical in the a fraction under the radical. We no longer have a radical in the denominator. But remember, rule number 1 says that we can't have any perfect squares underneath the radical as well. So square root of 8 can actually be simplified, so we need to break that apart. Keep in mind that's all over 5. And then we can take the perfect square out. So if we look at this, 2 times square root of 2 over 5 is the simplified radical form of that original problem. Okay, now we move to the fun stuff. And you know, when I say fun stuff, that's where it starts to get challenging. And we've looked at this a little bit already, so if you recall in the rules, it says that if you have a radical in the denominator, you have to get rid of it. Well, not always will it be a perfect square. So this is going to create a situation where we have to rationalize the denominator. Now, the idea of rationalizing the denominator is to multiply the expression by something equaling to 1. Okay, and when we do this, we're going to look for the bottom value in the denominator as a guide to what to multiply by. So if we look at this first example, we have 1 over the square root of 3. Well, since it's the square root of 3, we're going to actually want to use the square root of 3 because we know square root of 3 times square root of 3 is going to give us square root of 9, which is just going to be 3, and this allows us to clear out the radical. But because we're multiplying the bottom by the square root of 3, we also have to multiply the top by the square root of 3, and this gives us a fraction that is a form of the number 1. So what's happened here is the value does not change. This is important. We want the final answer to have the same value as the original problem. We just want it to conform to all of the rules of radicals. So square root of 3 over 3, if you were to put that in your calculator and get a decimal, should equal the same thing as 1 divided by the square root of 3, except now the form of our radical fits all the rules for simplifying radicals. So this is rationalizing the denominator. Now, in many cases, once you rationalize the denominator, you still have a little bit of work left to do. So if we look at set B, we've rationalized the denominator right here with the square root of 5 over the square root of 5, and then upon finishing this, we still have a 15 and a 5 in the fraction. Well, the radical square root of 5 kind of acts like a variable. You can reduce the 15 and the 5 without actually changing the radical, since it acts much like a variable does. So that can be reduced. 15 over 5 equals to 3. And so that is one example of something that will happen as well. Now, this last example is very important. Notice that when we had 4 times the square root of 2 in the denominator, we only needed to rationalize by the radical. It was unnecessary to include the whole number 4 to eliminate the radical. So you will run into some problems of this nature as well. So go ahead and take a time to do sample problem number 4. Pause video and see if you can work those problems real quickly. Okay, so if you've done this, square root of 4 over square root of 5, we need to rationalize the denominator. If you want to go ahead and simplify the square root of 4, you're more than welcome to go ahead and do that process ahead of time. So if I multiply the square root of 5 over the square root of 5, I'm going to take the square root of 4, which I know to be 2, and go ahead and finish that. So now 2 times the square root of 5. This is kind of like multiplying 2 times x. So if I multiply 2 times x, I would simply get 2x. So 2 times the square root of 5 is simply 2 times the square root of 5. So they don't combine together because they're not like terms. So that's going to give me 2 times the square root of 5 over square root of 5 times square root of 5 is square root of 25, which we know is simply 5. So we've rationalized the denominator using the square root of 5 over the square root of 5. That's a form of 1, and that allows us to simplify this radical. Part B, 3 times square root of 2, so we would need to multiply this by the square root of 2 over square root of 2. So we've rationalized the denominator there. So that gives us 3 square roots of 2. And square root of 2 times square root of 2 is simply square root of 4, which is going to be 2. So whatever the two radicals are, it's going to eliminate the radical and just give us the whole number underneath there. Lastly, square root of 6 over square root of 15. Remember, from the quotient property, this breaks up. However, with the square root of 15 on the bottom, we have to rationalize the denominator. So I'm going to multiply this square root of 15 over square root of 15. And this creates a little bit of a different scenario here. What happens is 6 times 15 is actually going to give us the square root of 90 on top. We've eliminated the radical on bottom through rationalization, but we now have a situation where we can we have to simplify the radical 90. So this is going to break up into the square root of 9 times the square root of 10 all over 15, which is going to give us 3 square roots of 10 over 15. Again, this looks like we might be finished, but remember, the square root of 10 is kind of like a variable here. The 3 and the 15 can actually be reduced into 1/5, and of course the 1 is understood, so the final answer is the square root of 10 over 15. So that is a more involved problem, but a lot of the radicals that you're going to have to deal with are a little bit more complex, like part C is. Okay, that basically concludes the simplification of radicals on their own. We're going to include some other radical properties which will help us get a jump start on future lessons, so that we don't have to go back and do this, such as adding and subtracting radicals. Now, If you notice in example 5, I really only have radicals in a couple of the sample problems, and the reason is I want you to recognize the pattern that has taken place here. If you think back to variables and combining like terms, the variables have to be exactly the same in order to combine the like terms. So if you look at sample part A, x and x gives us x. X squared gives us x squared. Remember, you cannot add these together. X plus x squared does not give you x to the third or anything like that. It gives you x plus x squared, since they are not like terms. So, when we have a radical attached to a number, it acts in many ways like a variable does. So you can see in part C, the square root of 3 and the square root of 3 is going to give us a square root of 3. So the 2 plus the 5 equals a 7 in every single case on A, B, and C. Now if you look, however, at part D, it's kind of like having a different term. It's kind of like having x and x squared. You cannot put those two together. So what's going to require of us is this. Taking the square root of 75 and breaking it up into simpler terms, and what eventually happens is we end up getting the square root of 3 on both parts that allows us to add it together. So see if you can follow along that pattern and those rules that you learned with variables and work on sample problem 5. Okay, if we look at part A, the first trickiest part about this problem is we're taking square root of 2 times square root of 2 minus square root of 2. And you're looking at it and it looks like there's nothing to subtract. But we have to remember, it's just like having an understood 1 in front of there. So now I have a square root of 2 term and a square root of 2 term on each of them. And so I'm simply subtracting 1, which is going to give me, 2 minus 1, which is going to give me 1 times the square root of 2. And again, since the 1 is understood, I can simply say square root of 2. So it's going to be 2 minus 1. On part B, we have square root of 6, and square root of 6 is our common term. So we're simply taking negative 2 minus 3. So negative 2 minus 3 is a negative 5. And of course, we cannot lose our square root of 6. Part C, however, gives us a situation where we have one term and then we have a completely different term. So before we can combine these together, we're going to have to break the square root of 24 up so that we can get a square root of 6 out of it. So let's take a look at that process. Square root of 24 is going to break up into the square root of 4 times the square root of 6, which means we have square root of 6 times 2 times 2 times the square root of 6, which means we have square root of 3 plus square root of 6 plus 4 times the square root of 6, and now we have square root of 6 as our common term, and we can simply add the 3 and the 4 together and carry the square root of 6 for our final answer. Last but not least, we have a common term here, square root of 45 and square root of 45, so 3 minus 2 is 1, or an understood 1, so square root of 45. The problem, however, is the square root of 45 is actually not simplified, so we need to break this up and pull the perfect square out of there. And 3 times the square root of 5 is our final answer. Okay, so that's going to conclude our radicals review. And keep in mind that the premise of this radical review was mostly based around square roots and the fact that the square root is understood in the radical symbol. But however, we will be using higher degree radicals as we go on later in the semester. So simplifying radicals is going to become a very important part of your solving quadratic equations. So we'll be using this quite a bit. So be sure to learn this well. If you need to go back and re-watch any parts of this video to master this, that's going to be extremely important. Okay.